So we have the last session today for this vector integration. We are going to see three important theorems from vector integration known as the Stokes theorem, Green's theorem and the Gauss theorem. Okay, the sequence is like this. In Stokes theorem, we use a single integration. In Green's theorem, we use a double integration. And in Gauss theorem, we use a triple integration. So the theorems we are going to learn in that sequence only. In the first theorem, we have to evaluate a single integral, line integral, and how to evaluate line integral that we learned in the last session only. We do this line integral in a parametric form. Next, we have a Green's theorem. In Green's theorem, we do the double integration. Okay, and in Gauss theorem, we do the triple integration. Generally, these integrals are simple to evaluate in that theorem. Okay, we'll come to that. Okay, so the first theorem is regarding the first theorem actually gives us the relation between single integral and double integral. See, this single integral is known as a line integral and double integral is known as a surface integral. For example, right now, one surface is drawn here. Okay, so this is a 3D surface. So surface can be a two-dimensional surface. Two-dimensional surface is like XY plane. Okay, the XY plane is one of the surface, plane surface there. But right now this surface is a curved surface, that is 3D surface. So the surface should be the open surface. You will see this surface is open from the bottom. So that surface have the boundary, and that boundary is written in terms of the curve C. Okay, this C is the curve and that is a boundary of the surface. Surface S. DS is a very small area of that curved surface there. And that n cap is a unit normal vector perpendicular to the surface at that point. Okay. So that about the things that we have for surface. Now, this Stokes theorem, we are dealing with the Stokes theorem. The Stokes first important thing you should remember, Stokes theorem is for the open surface. Meaning of the open surface is like a hemisphere. Okay, you have the box, but suppose it is open from the top. Okay, so that should be the open. It should be the open. Then it is open surface. Means it should not be a closed. Closed surface means like a ball. Ball is a closed surface, or you can say a sphere is a closed surface. So that should not be the surface. So when the surface is open, it have the boundary, and that boundary is a C. And now Stokes theorem tells us the relation between that the integral over this boundary, the single integral over this boundary is equal to a double integral over that surface. Okay, over that surface. That is a relation. So let I show you that relation. So here is a statement of the Stokes theorem. It is for open surface, and you can remember a double integral of a normal component of curl F bar. So this del cross F bar is curl F bar. So this is and dot product with n cap. So we say a surface integral of a normal component of curl F bar is equal to the line integral of F bar. Is equal to the line integral of F bar. Now this RHS is not new to you. We already learned in the last session. This is just a work done. Okay, work done or line integral. So indirectly, the Stokes theorem transforms the double integral to a line integral, or it gives us a relation between double and single integral, where the amount of normal vector field passing out from the surface S, the amount of a normal vector field passing out from the surface S is equal to the circulation of that F bar over the boundary. Circulation of that F bar over the boundary, or the line integral of F bar over the boundary. That is the meaning. So no need to by heart entire statement. Only this mathematical formula is important for you, and you should know the meaning of each and everything. So this del cross F bar is a curl. N cap is a unit normal vector to the surface. DS is a very small area of that surface. So sometimes n cap into ds, this together written as a ds bar. Okay, n cap into ds is written as a ds bar. And every time we never evaluate the LHS, only we evaluate the RHS there. Now in textbook, remember, in a textbook you have two types of a problem. Type 1, verify Stokes theorem, and type 2, evaluate using a Stokes theorem. So in our syllabus, if you see the syllabus, if you see the course handout, okay, it is a clearly mentioned only evaluate type questions will come. Evaluate the double integral using a Stokes theorem. That means we never do the LHS part. We never do the double integral of del cross f bar dot n cap ds because it is lengthy to evaluate. So instead of that, we just evaluate the line integral. Okay. Any doubt in the statement? Anyone?
No, sir.
No.
No,
Okay.
sir.
Good. So come to the question. You'll find it's very simple now, and it is a repetition of the yesterday's session only. So okay, the line integral is easy to evaluate. Because of that, we evaluate only the line integral. Okay, that is another important point. Yeah, come to the question. The question is now the vector f bar is given, and the question is evaluate this double integral. First thing we should know, this is the left hand side of a Stokes theorem. This is LHS of a Stokes theorem. So this S is the open surface. Okay, over the open surface of a cone is written. Now nowhere you have to draw a 3D drawing. Okay, 3D diagrams you don't have to draw anywhere in the exam, but it is just for your understanding. I will draw it here. Now this is the cone that we are given. Now how it is a cone, let we see. The first one, let I draw the coordinate axis. Say this is a y axis, this one is a x axis, x, y, and say this one is a z axis. Now if you put say z equal to 0, what you will get? If you put z equal to 0 in the equation of the cone, what you will get?
Circle.
Square
Square
plus y
plus
square
y
equals
square is
4.
equals to 16.
Yes, a circle of radius 4. That's correct. X square plus y square equal to 16. Someone already told. That's a good thing. So this is the circle that we get. So circle, I will say x square plus y square equal to 16. This is a circle completely in a xy plane. Now, when we put both x, y 0, if we put both x and y 0 in this equation, we get z is equal to 4. So we get, suppose this point is say 0, 0, 4, because when x and y are 0, z is 0. So minimum, so the circle is above xy plane. This is above xy plane. XOY plane means x, O is origin and y, XOY. So above xy plane. So the cone is like this. I'm not good in the drawing, but okay, roughly you will get the idea. This is the cone that you have. So here is the curved surface, yes. This is the curved surface S of the cone, and we have to evaluate actually this integral on the curved surface of that cone. Okay. So Stokes theorem tells us that this double integral is actually the equivalent to evaluating the line integral over this circle. So we are not going to evaluate this LHS part because getting n cap for this surfaces is a difficult, it is lengthy. Then you have to take a dot product, then you have to project ds on xy plane, and then you have to integrate. It is a too lengthy calculation. So generally it is never done that way. So it is done the line integral only. So let I show you. First step, we should say by Stokes theorem. So by Stokes theorem, we started a solution now. We write a statement. Stokes theorem says that double integration of del cross f bar dot n cap ds is the line integral f bar dot dr bar over the curve C. And we know f bar dot dr bar is integral f1 dx plus f2 dy plus f3 dz over C. So what should be the next step then?
Limit.
First, we'll replace this f1, f2, f3. We'll replace the values of f1, f2, f3 in the line integral. So the next step, I replace f1 is x minus y. So this is f1 dx, this is f2 dy, and this is f3 dz. Now tell me the next step.
Parametric.
Yes, we should move to the parametric form. So what is the curve first? In this case, the curve is
Circle.
circle. So what is the parametric form of that circle?
A cos theta
X
is
is
sin
equals to
No,
a
no,
cos
it's not
theta,
a
y
cos
is equals
theta.
to a sin theta.
4 cos theta, 4 sin
4
theta.
cos theta
Four
and
sin
4 sine theta are the correct answers. Very good. So x is a 4 cos theta, y is a 4 sine theta, and then we have the dx and dy. We'll replace it. So this is the circle that we have because in xy plane, z is a 0 and x square plus y square equal to 16. That's the equation of the curve C. So for this curve, x is 4 cos theta, y is 4 sine theta, z is a 0, dx will become minus 4 sine theta d theta, dy become 4 cos theta d theta, and dz is a 0. We have to just replace all these values in this integral, and we get the value of integral like this. So just f1 dx, f2 dy. F3 dz is not written. The reason is z is a 0, dz is a 0, so this term is not exist there. Okay, so just a replacement. If we simplify now, after simplification we left these terms. Okay, now can you tell me which terms integration goes to the 0? Which terms integration goes to the 0? There are three terms.
Minus 16 sin theta
Minus
cos
16
theta.
sin theta cos theta.
What about first term? Is it 0 or not?
64
Zero.
cos cube
Yes,
theta.
Yes,
sir.
it is a
First term is
0.
0. Third term is also 0.
And third term is also 0. That's a good
64
rule.
cos cube
Okay,
theta.
so see, when you use a property, how much calculation you reduce? Okay, otherwise, if someone is not interested to use a property, you will unnecessarily waste your time to evaluate these two integrals there. Okay, and what about this middle term then? What about middle term? How
So
to?
2 multiplied by 0 to pi 16 sin theta.
No. How 16 sine 3?
Sir, we can use beta function.
Yes, sorry. Someone said 4 times. Nah, 4 times. That is correct. Yeah. It's
Yes, sir.
first you have to convert it. 4 times 0 to pi by 2. Good. So because it's an even power and this 16 sine square theta d theta, that's only left. Correct. And now
We can use Wallis form.
yes, this 4 into 16 as it is. And by Wallis formula, we can say n minus 1 upon n. So 2 minus 1 is 1. N minus 1 upon n into pi by 2. Is it? So
Yes, sir.
the answer is a 16 pi then. That's the end of a question. 16 pi is the answer. Okay, got it? So this is the value of that surface integral. The value of this surface integral is a 16 pi. Got it? Any doubt? So everywhere we have to do this thing only.
Sure.
Yes.
We can treat sine square theta also as 1 minus cos 2 theta upon
Yes.
2.
Why not? I generally says that we have multiple ways. You should be smart enough to get the answer quickly there. So if you go for 1 minus cos 2 theta upon 2, you have to do the calculation. You have to integrate it. But better, the smartest way is you should use the rules. Okay, if you are able to remember it. If you don't, if you're not able to recall that rule, yes, obviously you don't have alternative then. You have to go for 1 minus cos 2 theta. Similarly, this also you can evaluate by converting cos cube theta into cos 3 theta. You can evaluate, but your answer definitely come a 0 because that's a rule. It's a universal property there. What it?
Yes, sir.
How cos cube theta is a 0? Please explain. Okay, already we discussed about that in the last session. There is one property that I told in the last session only, and that property is integration 0 to 2 pi sine raised to m theta into cos raised to n theta d theta is a 0. Okay, this 0 if m or n odd. So in case of this cos cube theta, the power of cos is odd and sine raised to 0 is there. So at least n is odd. As n is odd, the value of this value of the integral of this term is a 0 there. Got it? By the property, I'm not going to prove this property. Okay. The proof is very easy there. There are a number of ways to prove that, but this is not part of the syllabus there. Is that clear?
Sir, what is this formula called?
This formula, these are just trigonometric properties there of definite integral.
Okay, sir.
Okay, so actually it is very easy to prove this geometrically. Geometrically, we can prove this property very easily. Okay, let I explain in 2 minutes. Okay, because few of the students have the problems here. So see the graph of sine x. The graph of sine x on 0 to 2 pi. Can you observe something here? On 0 to 2 pi, the
Positive
graph of
integral is equal to negative integral.
yes, you will observe the net area under the curve is 0. Got it?
Yes, sir.
So integral
Yes,
0
sir.
to 2 pi, integral 0 to 2 pi sine x dx is a 0. Integral 0 to 2 pi sine x dx is 0. In the same way, if you see the graph of cos x, the graph of cos x go like this for 0 to 2 pi. And you'll observe this net area, because this is the positive area, this is the negative area, and net area is a 0 again. So integral 0 to 2 pi cos x dx is also 0. So we seen here, when there is an odd power, when there is a sine raised to 1 is there, cos raised to 1 is there, and the integral is coming 0, is it? Now let me draw the graph of sine square x. Can anyone guess what should be the graph of a sine square x? Yes, anyone?
The graph which is below the x-axis will also come up.
No, the graph of sine square x on the range 0 to 2 pi.
Only in the positive direction, both of them like
Okay, let I tell you.
rounded
The
you.
graph will shrink, sir.
No,
Both of them
it
will be
will
up
it
on the
will
upper side.
yes, both upper side. That is the correct answer there. Okay, you can see here indirectly it is a point by point multiplication. So sine square x means sine x into sine x. So 0 into 0 is a 0. So this is 1. Okay, this is 1. So this is a sine pi by 2 into sine pi by 2. That is 1 into 1 is 1. So this point remain 1. Again sine 0. 0 into 0 is 0. So this side the graph goes like this only. Okay. Now come to that side. So sine 3 pi by 2 is a minus 1. Sine 3 pi by 2 into sine 3 by minus 1 plus 1. Is it? And sine 0 0. So this side the graph goes like this. So this is the graph of sine square x. This is the graph of sine square x. I hope you got it. And you'll observe the area under this curve from 0 to 2 pi become 4 times 0 to pi by 2 that we used here. Sine square theta we use 4 times there. Is that clear? Don't go in the detail. These are the properties. Geometrically you can prove mathematically also. Just remember that is one property of definite integral there. Okay. Can we move to the next then?
Yes, sir.
Yes, sir.
Okay. So question number 2 is on the screen now. So it is exactly similar question. We have a f bar. We have to evaluate the surface integral over the surface of a paraboloid. Yes, Jappy. The problem. They don't know what they are doing. Okay. So this is the surface integral and we have to evaluate on the surface of a paraboloid. So instead of cone, it is just a paraboloid there. So these are 3D surfaces. Nowhere you have to draw it. Already I told. But just for your understanding, I'm showing you the graphs here. No need to draw these graphs in the exam. Just for your understanding. So what is the base? Yes, anyone? The base of this
Circle.
paraboloid, circle again. You put z equal to 0. You get x square plus y square equal to 4.
Radius 2.
So this is,
Radius
yes,
2.
a circle of radius 2. So x square plus y square equal to 4. That's the circle. And you put again xy as a 0, z is 4. So this is suppose 4. So it is a 0, 0, 4. And this is a paraboloid. So it is, there will not be like a slanted lines. There will be like a parabola here. There will be a parabola here like this. Okay. So this is the parabola there with whose axis of symmetry is the z-axis there. And this parabola is rotated about z-axis. So it become a 3D figure. That is a paraboloid. So again, we are not interested on the surfaces. We are interested on the base. So we mainly move on calculation. First, we'll say by Stokes theorem, the statement is surface integral is equal to the line integral. We replace the values of f1, f2, f3 there, and the circle, in this case, circle is the curve C is circle of radius 2, z is 0.
2 cos theta, 2 sin theta.
Correct. X is 2 cos theta, y is 2 sin theta, z is a 0. That's a parametric form. The values of dx, dy, dz are on the screen here. We replace these values and we get the answer as a minus 4 pi. Directly I written the final answer. You can cross check exactly similar rules that you have to use it. That integration 0 to 2 pi over for a sine and cosine power is a 0. If at least sine or cos power is odd, then it is 0. And if both are odd, it becomes 4 times 0 to pi by 2. And then the Wallis formula. Okay, I hope there should not be any doubt here.
No, sir.
Okay, so that about your Stokes theorem. So Stokes theorem is indirectly in the Stokes theorem, we have to do the calculation of that line integral only. That is work done. Okay, it is a similar to that only it goes. So it's not new there. But we'll move to the particular case now.
Excuse me, sir.
Yes.
Then the question it is written above the plane z is equals to 0. If we integrate below the plane z is equals to 0, it will be 0, right?
No, it is a below z equal to 0. First of all, if you take the surface below z equal to 0, the surface will be open from both the side there. Is that because this paraboloid below z axis, so below xy plane, z equal to 0 means below xy plane. It is open from the two side there, and generally such questions cannot be solved that because see we should have a surface which have one closed boundary, only one closed boundary there. Okay, then only the question is of that Stokes theorem there. Got it? Are you understood or have issue?
Yes, sir. Yes, sir. I got
Okay,
it.
so we should have one surface which bounded by one boundary only. And what happens if you take open cylinder? If you take open cylinder, it have the two open boundaries. Then then surface integral of that cylinder we cannot solve it. We can solve that surface integral of cylinder provided it should be bounded from one of the side there. Okay, one of the side there. It should be open only from one side there. Okay, so here we are going to see now a particular case of a Stokes theorem. So second theorem in our syllabus is a Green's theorem. This Green's theorem is a particular case of a Stokes. What is the difference then? The difference is the Green's theorem is applicable to again open surface, but that open surface is a surface in a xy plane only. That is a plane surface. It is a plane surface. It may be a region in xy plane. Okay, it may be a region in xy plane. That is the difference. So we should have okay, let me see how we start to get the statement of Green's. We know the Stokes theorem is this one, double integration del cross f bar dot n cap ds is equal to integral of f bar dot dr bar over the curve C. So this is the statement of the Stokes. Now if our surface is like this, suppose the surface is the region R here, that is in xy plane. So that region is a plane region that is in xy plane. So if region is in xy plane, what about n cap? N cap is along a z axis, is it?
Z
So n
axis.
cap is a k cap. Okay, so we take n cap is equal to k. N cap is a k. So n cap is fixed for the plane surface that is in xy plane. What about the value of a ds? A small area in xy plane ds. Can we write it as a dx dy? Okay, because small area in xy plane can be written as a dx dy because it's a flat area.
Yes, sir.
So yes,
sir.
ds can be written as a dx dy, and cap is a k cap. And now if okay, so that about the first two things. And now we have to compute this del cross f bar now. Let me calculate del cross f bar so that we can take a dot product of del cross f bar with n cap there. So by definition of curl f bar, by definition, so here is few things written. For a region in xy plane, z should be a 0. So as it is a region in xy plane, so z is a 0, dz is 0. So as dz is 0, this third term, I will remove JAPU now. Okay. If you're not able to handle your mic, I will remove. This is the last warning now. Okay. So this one is a for the surface is an xy plane. Z is a 0, dz is a 0. Okay. N cap is k, and this ds is a dx dy. So these are the things that we'll use for the proof. This proof will not come in exam. I will tell you the proof at the end. You require only the mathematical formula of a Green's only. I will tell you that at the end. So the next thing is here. This del cross f bar. This del curl f bar, by definition, it is a determinant evaluated. Okay. Now, can you tell me what should be the value of del cross f bar into n cap? What should be the value of del cross f bar into n cap here?
Sir, dou f2 by dou x minus dou f1 by dou y.
Dou I, correct. Very good. So this is a curl f bar. This is a curl f bar vector, and we have to take dot product of curl f bar with k only. So only k dot k is 1, I dot k is 0, j dot k. So this term only remain there. Okay. Yes, I will tell you what is the difference. The difference of the previous theorem and this theorem is this Green's theorem is only applicable to the plane surface. Stokes theorem can be applicable to here also, but you have to do some extra calculation there. So better when the surface is a plane surface, that is an XY plane, we use a Green's theorem. Okay, so when the region is an XY plane, indirectly I will tell you. Okay, because of this now, if you replace all these values in this statement, we get a statement of a Green's now. So I'll show you the statement of a Green's here. So the statement, this is the Green's theorem. So Green's theorem, see, as dz is 0, z is 0, dz is 0. So this line integral left only integral f1 dx plus f2 dy over the curve C. Okay, so the line integral only this part left, and this LHS is written as double integral of dou f2 by dou x minus dou f1 by dou y. This is del cross f bar dot n cap, this value, and ds is the dx dy. And now in general in the Green's theorem, this double integral is easy to evaluate. Why this double integral is easy to evaluate than the line integral is because the boundary is not made up of a single curve. Suppose boundary is a circle. Suppose the boundary of the region is a circle, then the line integral is also easy to evaluate because only one integration you have to do it. But suppose the boundary is a square or a triangle, what you have to do it, you have to evaluate the line integral on each boundary separately, like C1 plus C2 plus C3, and that become lengthy. Because of that, in general, in the Green's theorem, we use double integral to evaluate because there is a single double integration that you have to evaluate in the Green's theorem. Any doubt?
No, sir.
Okay, so what you have to remember on this slide, this last statement only. This is the important thing that only that you have to remember. The Green's theorem is the relation between again a single integral and double integral, but in the Green's theorem we evaluate a double integral. In Stokes we evaluate line integral. In Green's we evaluate a double integral there. That you should keep in mind. So next, see the question now. The question is, we have to evaluate this line integral over a rectangle. Now, as it is a rectangle, the rectangle have four different boundaries. Okay, four different straight lines as a boundary. Because of that, it's better to convert this line integral to a double integral and evaluate it. So this is the integral like f1 dx plus f2 dy. So indirectly we have to integrate f1 dx plus f2 dy. So in solution, the step number 1 comes by Green's theorem. The line integral f1 dx plus f2 dy is a double integral dou f2 by dou x minus dou f1 by dou y dx dy. Now compared to this integral, what is the f1 and f2? So the f1 is here, e raised to minus x sine y, f2 is e raised to minus x cos y. So these are the values of f1, f2 we get by comparison to these two line integrals only. Now what is the dou f2 by dou x?
Minus e raised to minus x cos y.
Correct. Minus e raised to minus x cos y. And what is the dou f1 by dou y?
E raised to minus x cos y.
E raised to
Minus e raised to minus x cos y. Same one, same answer, is it? So
No, sir.
how no? Huh?
So e raised to minus x cos y.
Sir,
Negatively
sine
I
y
will
is
Yeah, yes, you are correct. So let I check. So it is a minus e raised to minus x cos y. Okay, you are correct. So it is just opposite sign. Yeah, good. But here middle there is a minus sign. So this become minus and this is minus and that become 2 times. Is it? So is it
Yes.
clear? Okay, good.
Yes, sir.
Now our aim is to evaluate this double integral over a rectangle. Okay, over a rectangle, and the rectangle, the vertices were given, 4 vertices of rectangle. Can you guess the limits of x and y now from these vertices?
Sir, x 0 to pi and y 0 to pi by 2.
Yes, that's one. So you'll observe these are the 4 corners of the rectangle. So x, these are the x coordinates. So minimum value of x is 0, maximum is pi. Minimum value of y is a 0 and the maximum value of y is pi by 2. So limit of x should be replaced from 0 to pi and limit of y 0 to pi by 2. Without diagram, you can give the limit. Okay, no need to draw the diagram. So these are the limits. So integral of this minus 2 kept constant as it is. Integral of e raised to minus x is a minus e raised to minus x with the limit 0 to pi, and integral of cos y is a plus sine y, is it? And that is 0 to pi by 2. Put upper limit and
Yes,
lower
sir.
limit. What is e raised to minus pi? You have to keep as it is. What is e raised to 0?
1.
E raised to 0 is 1. Sine pi by 2, 1.
1.
And sine 0,
1.
0.
0.
Okay, so
0.
these values we replace and we get the final answer. That's the end of a question. These questions are coming for 5 marks if they come, okay. But generally, remember, work done, I will tell you, work done, Green's theorem, Stokes theorem, and Gauss theorem. Together, these 4 articles have the 5 marks weightage in final exam. So, generally, one question only will come from this, from work done to the Gauss theorem, 5 mark question, okay. So these are very simple examples, but only important thing, you should start with the correct formula, and you should use the correct calculation.
Sir,
Yes.
so using Green's theorem, can we calculate any double integral in xy plane, right? Like earlier we solved questions when we started our double integral, like area between y-axis, parabola, and y equals to x. So we can calculate using Green's theorem also.
Means you are saying that we started integral calculus at the first part, that examples.
Yes, sir. Like we
No,
solved double integral, right?
you not understood the difference here. The difference is Stokes theorem, this Green's theorem gives us just relation between line integral and double integral. Okay, and that is a totally different topic where there is no such a relation that we have, is it? Because suppose you have okay, so you are saying whatever the regions we have there and we have boundaries there. Is that you are asking about that?
Yes, sir.
But you have the region and the boundaries, but you should have then this vector f bar there. If you have the vector f bar like this one, then you can do it definitely. Yeah. Okay. You see what are the requirement to solve this problem? The problem, you should have some region which should have the boundaries only. Okay. So yes, all that questions we learned in integral calculus. We have some region and we have some boundaries there. Okay. But we do not have the integrand in this form. If the integrand is in this form, then you can convert that line integral to the double. Or if you have the double integral, and if you know their f1 and f2, and you able to convert the double integral in this form, you can do it. Why not? Got it?
Okay.
Okay.
Yes, sir.
Okay, so that about the greens. So probably there is one more question here, but I think I will, whether I solved it or not, I will check it. So you will clearly observe for this integral, what is f1 and f2? Here is f1, okay, and this is f2. Got it? And
Yes, sir.
and we have to evaluate over the region bounded between these two curves. So again, by Green's theorem, yes, it is solved here. Line integral is converted to the double integral. Now this is the question in that form, whatever we done in integral calculus, that form only. But the difference is there. This f bar is given. Without f bar, you cannot start there. You cannot start by Green's there. And now dou f2 by dou x is calculated. What is the dou f2 by dou x?
2y.
And dou f1 by dou
2y.
y? That is also 2y, but
Minus 2y.
minus
2y.
2y.
Minus
Correct.
2y.
So this become 4y. And now the limits taken. See, I actually I should, okay, already now the limits in front of you, but without diagram I taken the limits because I know which curve is on the left side and which on the right side. Here the diagram is required to get the limits. Otherwise, you cannot able to get the correct limit, because some student have the doubts here. They generally think this y square should be upper limit and y should be lower, and they give the wrong there. So that is not correct. You will observe in this case y square indicates symmetry is about x-axis. So this is the first parabola. Okay, and then y equal to x. Something like this. This is the region R there. And the strip is taken, you can take any strip there, horizontal or vertical, but right now I observed x is a y square and x is a y, so I taken horizontal strip there, and by the horizontal strip The left hand touches to x equal to y square. The right hand touches to x equal to y. And obviously the minimum value of these are 0 to 1, 1. Okay, so these are the limits given there. So limits given mainly from the diagram there. Is that clear?
Yes,
Yes,
sir.
sir.
And now the matter is only to evaluate this double integral by when we integrate it with x, treat y like a constant and do the integration. So 4y dx integration is x, y square to y. So this is the inner integral evaluated, and then the outer integral and upper limit and lower limit. You will have the answer as 1 by 3. Got it?
Yes,
Yes,
sir.
sir.
Okay. So that about the second theorem now. The first theorem we see in the Stokes where we evaluated the line integral. This theorem just we see in the Green's theorem. In Green's theorem, always we evaluate a double integral. That's better to evaluate. Okay, because there are multiple boundaries. In this case also there are two boundaries. You'll observe otherwise if you have to do the line integral, you have to do the line integral on parabola as a C1, then line integral on the straight line as a C2, and then you have to add these two line integrals and then you get the answer. But Green's theorem helps us, instead of evaluating the two line integral, we done one double integral only and we got the same answer. We always get the same answer there. That's why. Now last theorem. The last theorem is the Gauss theorem. This is known as the Gauss divergence theorem. First important thing, it is for a closed surface. Okay, surface should be a closed surface like a sphere. Okay, so that's only. So generally when the closed surface is there, yes, it can be done on a surface of cone, but cone should be closed. It should have multiple surface, but that surfaces should be there and it should be a closed from all the sides so that it should not be open from any place. It should not be open from any place. So that is the first condition. It is for a closed surface. And what it says, uh, surface integral of a normal component of f bar, surface integral of normal component of f bar is the same as the volume integral of a divergence of f bar. Volume integral of divergence of f bar. So the name is given as Gauss divergence theorem. So in Stokes, we've seen the curl there. In Gauss theorem, in divergence theorem, there is a divergence dot is there, del dot f bar is there. Okay, so that is a difference again. Again, the most important thing in Gauss theorem is triple integral is easy to evaluate. We generally do a triple integration in the Gauss divergence theorem. Surface integral is always difficult to evaluate in the Gauss theorem. Okay, because that surface is not a plane surface. If the surface is plane surface, generally that is only in greens, and there we evaluate it. But when the surface is a curved surface, that is very difficult to evaluate. There are a number of things we require. Because of that, we generally avoid it. Okay, I hope you understood, and this is the important thing. In general, we evaluate the volume integral. Okay,
Yes,
so
sir.
we'll move to the question then. One question only, I think. Okay, so already I written here everything. I think by mistake it came. Sorry. No. Okay, forget it. So the question is evaluate double integral f bar dot n cap ds over the surfaces by a divergence theorem, and vector f bar is given where S is the surface of the sphere of radius a. Okay, that is the thing. So step number one, we should say by Gauss theorem, double integration f bar dot n cap ds is a triple integral del dot f bar dv, and now del dot f bar is calculated dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Is that clear?
Yes,
Yes,
sir.
sir.
What should be the next step now? There is one silly mistake few students do. Let I check how many of you give me that answer. Yeah. What should be the next step?
Limits.
Limits. Okay. Limit is okay. That's correct. Uh, can anyone have any other way to solve this triple integral? Yes. Okay. No one is answering. Okay. No issue. Yes, Sahil.
So can we solve it by polar form?
Polar form. Okay, yes, we have to go to the polar only, because whenever there is a circle, a sphere base that is an xy plane is a circle, and we should go in polar. That is also correct. But what is the silly mistake that few students do, I generally observe? They put this x square plus y square plus z square as a square directly here. They think, yes, it is given in the equation only. Why should not we replace it? Yes, you cannot replace. That is a silly mistake that you will do it. The reason is this x square plus y square plus z square is a square is only on the surface of the sphere, and this triple integration is not only on surface. The triple integration is over a solid. It comes from origin to the surface. Okay, so you cannot. It is not a square only. It is 0 to a square. This x square plus y square plus z square takes the value 0 to a square there. So the next thing that we have, we have to find out the limits for this triple integral. How we evaluate this triple integral? Yeah, 3 is a constant. I will take, okay. So this 3 is a constant as it is. This is the triple integral of x square plus y square plus z square. Actually, this integral becomes very simple with a spherical polar coordinate, but I avoided that this time. Okay, so without spherical, I will show you. Just the step number 1 we already discussed. Whenever we have to evaluate triple integral, we generally find the limit of z first, so that we are familiar with that surface in the xy plane then, or projection of that solid in xy plane. Now you will observe that is a sphere. The sphere is in entire all 8 octants there. Okay, everywhere on this. So what we have to do it? Can you use a symmetry? How many times you can write it? 4 times, 2 times?
2 times, sir.
Okay, you are interested to take 2 times. Then when you take this 2 times, okay, when you want to take 2 times there, that means you are taken a hemisphere, is it? You converted that solid to the hemisphere. So if it is a hemisphere, what will be the minimum value of z and maximum value of z over that sphere?
0 to a, sir.
0 to a.
No, it's not correct. 0 is correct, but upper limit is not a. If you are taking a, you are just moving on that z
Under
axis.
root a square
Yeah,
minus
Under
x
root
square
a square
minus y
minus x
square.
square minus y square.
This is the correct
Minus-
answer. Root of a square minus x
A
square
square
minus
minus
y
x
square.
square minus.
Good, very good. So this is the correct answer. I hope everyone got this step. Anyone have the problem to get the limit of z here?
No, sir.
Okay, I will draw a rough diagram. Otherwise, those who are not understood, but it is not required. So this is actually the case. This is x, y, and z, and on this case, we taken only this part of the sphere, upper part of the sphere, and because of that, it we written it is a two times, and here is if you observe, if you take something like this, this is in xy plane. So in xy plane, z is the 0, and upper side z is that square root of a square minus x square minus y square, that way. Okay, so this way we got a limit, and now we'll proceed here. This 3 into 2 is a 6, and we have to integrate it. Integration will go like this: x square z plus y square z plus z cube by 3, and the limits of z 0 to root of a square minus x square minus y square dx dy. You have to put upper and lower limit. So this comes 6 times the double integral. We can write like this also. This is x square plus y square, x square plus y square into z is there. So that z is a root of a square minus x square minus y square plus this a square minus x square minus y square bracket raised to 3 by 2, is it?
Yes, sir.
Upon 3.
Yes, sir.
Okay. Upon 3. And if you put lower limit, it is a 0, obviously. That is a dx dy. Now, I want the limit of x and y. Yes. Or is it, we have to proceed as it is or something else? Already I got that answer actually.
Sir,
So we'll
limit
change it to
of
polar
x.
form.
We should go to the polar. Yes, the most important thing, we should move to the polar form. So if we move this to the polar form, this 6 times a double integration. What about x square plus y square?
R.
R.
It is
R,
r square. It is not only
R
r.
square.
yes, R square.
R square into root of,
A square
Root
minus
of
Square
A
minus R
square
Square
minus
minus
R
R.
minus R square.
correct, plus a square minus r square
Minus
minus
R
R
R square.
square power 3 by 2 upon 3
R
R
dr
dr
theta.
R
dt.
dr d theta.
RDR theta.
and limit of r
0 to
0 to
0
A.
to
0 to 1. A.
a this
and theta 0 to 2 pi.
0 to
0
pi.
to 2
2
pi.
0
pi.
to 5.
2 pi.
Correct. Now this is only integral that left. We should evaluate it, and to do this integration, there are multiple ways now. Or is there any way? Yes, the Gauss theorem sometimes goes like this, a little bit lengthy because it's a triple integral. And to integrate this, yes, one of the way, yes, you can do that. R square equal to tu. Also, you can replace that r dr can be replaced as dt by 2. Is it?
A square minus R square also we get T.
Yes, a square minus r square is equal to t. That is also the better substitution. That is also correct. Okay. So choice is your. Can you do the remaining steps your own?
Yes,
Yes,
sir.
sir.
Okay.
Yes,
Yes,
sir.
sir.
Because it is just mathematical part left. I want only to show you how that surface integral is written in the volume integral, and volume integral is nothing but is just our normal triple integration. We do it. Actually, this integral becomes very simple by a spherical polar. In spherical polar, there you have replaced actually. Okay, I'll not go in that detail. That x is r sine theta cos phi, y is r sine theta sine phi, z is r cos theta, dx dy dz is r square sine theta, dr d theta d phi, and so on. There are many more things there. Okay, so no need actually to use a spherical. You can do all the examples without spherical polar. So better you should focus. First, find the limits of z. First, you find out the limit of z by by taking the symmetry and divide the solid above xy plane. Okay, take a solid above xy plane, because whatever the solid we have above xy, that is same solid is below xy, so we taken it 2 times z equal to 0 to this one. That is the main part. And then once we integrated with z, the double integration in xy plane, we done it here. Okay, converting in a polar there.
Sir,
Okay.
if we take four symmetrical paths, then will the limits change?
If you take four symmetrical part, means you want to divide this solid into 4 parts there.
Yes, sir.
So the 4 part means, see, first of all, when this just we taken xy plane divides the sphere into 2 parts, is it? Now when you want to write 4 times, so which solid you are going to take it? Means whether you are going to take from positive x-axis to negative x-axis only. That means okay, that way actually you can take 8 times also. 8 times means only the part of the sphere in the first octant. That means positive x-axis to positive y-axis and positive y-axis to positive z-axis. And in that case, if you write here 8 times, if you write 8 times, the limits of z will be the same. The limit of z will be the same. Only here the situation will come. It become 0 to pi by 2. Okay, because or you can do it here also. You can observe it is 4 times 0 to pi by 2. 4 times 0 to pi by 2. So a little bit change in the limit, but the limit of x and y only will change. Mainly limits of theta only will change. Got it?
Yes, sir. Got it.
Okay, good. Okay, just a minute. Okay, so that about our vector calculus. Mainly I covered very important articles from